So let's get started. Yeah, so first, sorry about all the bug fixes on PSET 7. So yeah, maybe not a surprise. A lot of your homework problems, I basically make you prove various lemmas and results from old papers. And as it turns out, one of these papers I drew a lemma from wrote some stuff that was not quite right. And I sort of trusted them, and then when I looked into it, I was like, there's some mistakes here. And I emailed them, and yeah, so it seems that there were some small errors in their writing, but yeah, so like factors of m missing from places, etc. in problem 2. Okay, so I'll have to keep that in mind for the future. So today, what are we going to do? So let me move this out of the way. We're going to finish linked cut trees. Well, I'm just going to give you the analysis. In class, I'm going to show you log squared n amortized per operation. And on PSET 8, which is out, there is a problem that asks you to improve this to log n. Okay. Also notice on PSET 8, I skimmed the PSET 7, how much time did you spend on this PSET, and the number seemed kind of high. So right before I released PSET 8, I thought, maybe I should tone this down a little, and you can do one of problems 2 and 3. You don't have to do both. Finish link cut analysis. So so getting the log n is on the PSET. I'm going to show you log squared n. And actually, we're using splay trees. If you remember, in the auxiliary trees that we're using to store preferred paths, we used splay trees. So to get log squared n, you don't really need to use splay trees. Any kind of balanced BST is fine. But when you try to get log n, it's easiest to do it with splay trees, basically by using the splay access lemma we proved in lecture 7. If you remember, we had a specific potential function for splay trees, and we showed a certain lemma about its performance, right? Do people remember this? We defined a weight function on the vertices, and based on various weight functions, you can prove different properties. So if you define the right weight function for splay trees, and then pop that into the PSET, you'll get a log n amortized analysis. Anyway, so we'll show this in class, log n on the PSET. And then we'll say some things about min cost max flow. And there's a problem on the PSET related to this as well. And then today is going to be the last day when we do flow. There are only, I think, 3 lectures left after this, so I'll tell you about some other things. Okay. So if you remember last time, right, the way we implemented access, we had this subroutine called access, which was performed on a vertex. Basically, it makes the root vertex of the root tree of aux trees. And it did this by repeatedly splaying V and then connecting it to its preferred, to its path parent, and then now splaying again to make it the root of that. And it just kept splaying it upward, right? If people remember this. And then we had a couple other operations. We had, well, let me just write cut and link again. So cut, it first did access. Right, so now what's the picture here? V is in, V is here. If you remember, when you're accessed, you have no preferred child, right? Because if you are the last vertex touched in your subtree, then you have no preferred child. This is V. So it has no right children here. It just has some, maybe V is the path, is the path parent to maybe some people, but in its aux tree, it doesn't have any right children. And then it had some left children. And then we cut this, right? So at the end of a cut operation, V is in its own aux tree, in a singleton aux tree, right? So v dot left dot parent is none. And then v dot left is none. And then let me write the last one, link. I'm not going to write all the other ones. We'll just focus on these for the analysis. Link v to w. So v is the root of its represented tree, and w is in a different represented tree. And now w is the parent of v. We draw an edge from v up to w. That's what link does. So the way we implemented this was we did access v, access w. Now both of them are the roots of their respective tree of aux trees. And then now we need to just splice in v as a left child. So v dot left equals w, and w dot parent is v. Remember that the aux trees are keyed by depth, right? So the fact that w is my parent in the represented tree means that its depth is 1 less than me. So he's on my left subtree. Okay, so what we said last time is that the runtime of access is proportional to maybe something like 1 plus the number of preferred child changes. We call this PCC. Okay? Because we keep splaying v upwards in this tree of aux trees, right? And how many times do we have to do that? Not the runtime of access, but the number of iterations of, let's say, splays performed during access is something like that, right? Every time we have a preferred child change, we splay v upward. We merge with that new parent in the preferred path, and then we keep splaying upward until v is finally at the root aux tree. So what we have is the runtime of m operations is at most the cost of the splays, the worst case cost of splay, times m plus the total number of preferred child changes across all m operations. And this is, we know, this is definitely at most log n. I mean, wait, what's your question? Why is there an m there? So I just summed over all operations, so this 1 became an m. Yeah. So let's say preferred child changes in this access call. Whereas this is the total number of preferred child changes across the entire sequence of m operations. So what you're going to see, if you do that pset problem, you'll see that this is really kind of wasteful to say the worst case cost of a splay times the number of preferred child changes. You're going to see that kind of the total, the amortized cost of all displays combined is kind of on this order. Okay. Good. So we just need to bound okay. We just need to bound the number of preferred child changes, and we'll show that it's O of m log n. Okay. And that's why we get the m log squared n. So before I can do that, I need to introduce one more kind of analysis tool. Okay. So before we bound PCC, I want to define something. This is called the heavy-light decomposition. So just like we had the preferred path decomposition, this is some other way to decompose trees. Okay, but we're only going to use this. So with the preferred path decomposition, we actually use that to design our data structure, right? Because our aux tree contains preferred paths. With the heavy light decomposition, we're just going to use this as an analysis tool. We're not actually going to maintain it in our data structure in any way. Okay. So with display trees, we are getting amortized bounds. If you want to get worst case bounds, the ways that do that actually do maintain this explicitly in the data structure. But for us, we're not going to. We're just going to use it for analysis. Okay, so for a vertex V, define size V is the size of its subtree. The number of vertices in its subtree in the represented tree. And oh, do I have a scribe for today? Oh, okay, great. Okay. Good. So if we have the represented tree here, and there's some vertex that has some subtrees hanging off of it, let's call this V. Let's call this U. So U is a child of V. Okay. We say the edge UV is light if the size of U is at most 1/2 the size of V, and we call it heavy if the size of U is bigger than 1/2 the size of V, is at least 1/2 the size of V. Okay. So in our case, each edge in the represented tree has one of 4 types. Right? It can either be light or heavy, or it can be, and it can also be preferred or not preferred. Right. So just to set up some language, over the course of operations, we might create new. Well, in the course of operations, we might destroy some preferred children and create some new preferred edges. Destroy some preferred edges and create some new preferred edges. right? Meaning if we access something, if we access a vertex v, the root to v path is now the preferred path, right? Which means that some of the edges above, which used to be preferred, are no longer preferred if they were hanging off a different subtree. So we say that we destroyed those preferred edges and we created some new ones. Okay, so let's say if uv used to be preferred, let's call v is the parent of u. So if uv used to be preferred, but now wv is, then we say uv was destroyed and wv was created. Okay. So the first thing is, so we want to bound PCC. So claim is that PCC is at most, I'll define these, 2 LPCC plus M plus N, where this is light preferred edge creations. Okay. So I want to show you that this is true, and then we just need to bound this. So questions about anything? Oh, why am I calling it preferred child creations? It's just so it matches the acronym. Okay. So let's prove this. So first of all, whenever we create a preferred child, make a new preferred edge, that new creation of this preferred child is either a heavy creation or a light creation, right? So I just want to make sure we're all on the same page here. So here's the root. The root has some path down to W. W used to have, or I guess I called it V. V used to have some preferred child U, but then we did an access. Then we did an access on W, right? And then now this is no longer the preferred child, and then this is preferred. This is the new preferred, right? So we're all on the same page here. So I'm saying that this was a preferred child destruction, and this was a preferred child creation when we did an access. So we did an access somewhere in W subtree. Right? Okay. So this thing this is a preferred child change, so we should count it here. Now, it might either be, this new edge that we just created could be either light or heavy, right? That depends on the structure of the represented tree on the various sizes. Now, if it's light, okay, so proof, if WV is light, great, because we count it, right? And it definitely gets counted here. It is a preferred child creation, and it gets counted here because it's a light creation. Now, what if WV is heavy? Okay. There are two cases. In the first case, case 1, I'll say W is null. It might be the case that V didn't have a preferred child before, right? And then now that we access something in W subtree, now W is the preferred child. But how many times can this happen? Well, how can it be the case that V has no preferred child? Either this is the very first time we're ever touching V's subtree, right? But that can happen at most n times, right? So either this is first access in V's subtree. That happens at most n times across all V, across all time. This happens at most n times. Or the last access in V's subtree was either to V itself, that's why it has no preferred child, or it had one, and then we cut it off in a cut operation. Or last access in V subtree was to V, or we cut the previous preferred child. I guess actually, now that I think about it, the way that cut is implemented, then it would also be the last access in V subtree. Right? V would be the last access in its subtree. So really, it's only this case. But then, whenever we do an access on a vertex, we could imagine after we finish doing the access on that vertex, we hand that vertex $1. Okay, and then the next time that vertex V is ever in this situation where there's a heavy edge creation, then we could spend that $1 to pay for this. And the amount of dollars we're spending is M, one per operation, one per access. Does that make sense? Basically, we charge this to the last access on V. You look troubled. Is there a question?
So you're charging the last access to the last access?
No, I'm charging. So we're doing this heavy. We're in this case where we're creating a heavy preferred edge. Okay. And what I'm saying is, if we're creating a heavy preferred edge, and our parent doesn't already have a preferred child, because its last access was to V itself, then we'll charge this heavy edge creation to that last access to V. And each access will only be charged at most once in this way. Right? Because the next time we see V, it will have a preferred child, right? Namely W. Unless there was another access, in which case that access would get charged. So we actually didn't really need this because there's an access in there. So we charge to the last access on V. Okay. In case 2, is again going to be just charging. U is not null. So it actually had a preferred child before. So this edge WV is heavy. What can you tell me about UV? Can a vertex have 2 heavy children? No, right? Because what does it mean to be heavy? The size is strictly more than a half. This subtree has strictly more than a half of the children of the descendants of V. So it can only have at most 1 heavy child. So this implies we destroyed some preferred light edge. UV.
These are children in the represented.
Yeah, represented tree. That's right.
Is the represented tree necessarily a binary tree?
No.
So can't it have?
It can have many light children. Right? You can have lots and lots of light children, but you can only have one heavy child. Or you can have no heavy children. That's also possible. Right? But how many times can you destroy a preferred light edge? Well, it had to have been created at some point for you to destroy it. Right? So you can charge it to the time when it was created. So that's why I have a factor of 2 here. Do I have that factor of 2? Right? Okay, so that's that. So now that we have that in hand, let's look at the cost of cut, link, and access. Oh, because I want to wanted to charge the last access, right? So in this way, and okay, so I want to charge the last access, and then now the question is, how many times can any particular access be charged in this way? At most once. It'll be charged by the next heavy edge creation, heavy preferred child creation. So each operation is being charged in this way at most once. There are m operations, so that's an extra additive m. Is that okay? Okay. So now let's bound LPCC across, access, link, and cut. So access. Note access doesn't change the represented tree at all, right? Access only changes what's preferred and what's not preferred. So what's light and what's heavy doesn't change. Only preferred and not preferred changes. So as we walk back up the tree, changing these preferred child pointers, we just need to count how many of those new preferred child pointers is light, because we're only counting light preferred child creations. Now, on any route, on any path, on any route to V path in the represented tree, number of light edges is at most what? How many light edges can you have in a path from the root down to some vertex? Not log of the depth, log of something. Log of what? But yeah, so log of something. So what's the point, right? So first of all, how big can the size of a subtree be? What's the word? Give me any upper bound. No, just in period. So you have this represented tree. You have a vertex in the represented tree. It has some size parameter, right? The size is the size of its subtree in the represented tree. What's an upper bound on that? That's always true. N, right? You can't have more than n people in your subtree. And if you're following the light edge, the size is decreasing by a factor of 2. So in any path from the root down to anything, the number of light edges you traverse can never be more than log n. Right? So when you're doing an access and you're changing preferred children going upward toward the root, you're changing it along this preferred path. Some of those are heavy creations, some are light creations. But the number of light creations is at most log n, because there are only at most log n light edges on a path. And, okay, number of light edges log n. And what's light versus what's heavy doesn't change during access. That's it. So so that's giving us. Remember, the bound we're trying to get on PCC was m log n, right? So we know that there are at most m accesses. Each one is having at most log n light preferred child creations. So that's m log n. That's fine. So now let's look at link. Okay. So so what does link do? The first thing link does is it does two accesses, right? So let's say link on VW. It does access on V and access on W, right? So the LPCCs for the accesses are already covered by item 1 here. So we first do access V and access W. And then now what do we have? And then what do? We let's look at the represented tree. So W is somewhere in the represented tree. Let me, how should I want to write this? There's W. It has some subtrees hanging off. And then we also now hang off V. And what's the preferred path here? So what are the preferred paths? This path is preferred because we didn't access on W. And that actually goes all the way down to V. Okay. Good. So how many? And so what do I want to say? Now what can we say about so we already did the access on V and already did the access on W, right? That's already taken care of. But then after we do those two accesses, then what do? We add this edge right here, right? Okay. So what changes now is light versus heavy, right? So in particular, all the yellow edges here got heavier, right? And all of the old preferred children that used to hang off here got lighter. Okay. So maybe because they got lighter, that counts as a light. You might say, does that count as a light edge creation? Well, it's not a preferred child, right? So other edges hanging off got lighter, but who cares because they're not preferred, They're not preferred. But the yellow edges that got heavier, that might result in some heavy edge creations. But we're not counting heavy edge creations anyway, so we don't care either. Okay, so this bullet could be the source of heavy edge creations. We don't care. Heavy preferred edge creations, but we don't care about heavy preferred edge creations. This could result in light edge creations, but they're not preferred. So we also don't care about them. So this final edge that we draw is basically free in terms of counting LPCCs. We only had to pay for the two accesses on V and W before we did that linking operation, before we added the edge. Yeah.
So you say all the preferred edges got heavier. Does that mean they're necessarily heavy?
No, they might not be heavy.
So couldn't we have a light edge creation that's preferred?
So this was already made preferred by the access. So the access paid for that. Okay, and if it's still light now, it was definitely light before when we did the access. So the access paid for it. Right? Does that answer your question?
Well, and then V to W.
Oh, so maybe there's one more, but that's an additive one. I don't. Yeah. Good. Actually, I guess technically the way that we implemented link was, how did we? Yeah, actually, technically the way that we implemented link, this wasn't even in the preferred path either. Because we did an access on V, then we did an access on W. So V might have some preferred child. Oh, so now V doesn't even have a preferred child, because the last access in V subtree was to V itself. So that's actually the picture after a link. Does that make sense? So that's that. Now we just need to handle cut. What does this do? Remember, cuts off V from its parent W in the rep tree, represented tree. Okay. So what's the picture there? So the first thing we did was you did an access to V. So let's again draw this. Let's draw this represented tree. Okay, so that's W. V is hanging off. It used to hang off here, and V has a subtree, and then we cut that off. Okay. So again, after the access, we just change. Right after the access, we change what's light and heavy, right, by cutting this edge. Okay. So what changes? So some of the things here that hang off here. So edges hanging off this yellow preferred path got heavier, but they're not preferred, so we don't care. Even if they were preferred, I guess we wouldn't care because we don't care about heavy edge creations. But the edges in the yellow path now got lighter, right? They got lighter because we cut this out, right? So there might be some number of light preferred edge creations along this yellow path. Okay, are people believing me? But there can be how many can there be? Log n. Because again, it's a path. It's a root to leaf path. So in total, the number of LPCCs across M operations is of M log n. Okay, so that's it for the log squared n amortized bound. Are there any questions about this? Yeah, technically, I guess you should also. There were a bunch of other operations. There was find root, find min, all those other things. I mean, there's not much to say for those. You can go through and look at it yourself if you want, but these are the three, I think, ones that require the most work, and they weren't even that much work. So,
So the overall number of PCCs had an additive n, right?
yeah.
So you have to do for the overall time to go of n plus m log n, or
Yeah, so this implies M operations take time of m log squared n plus, I guess, n log n, because the number of PCCs was multiplying log n. Right. Right. So I mean, this is a kind of a sloppy. I mean, also it depends on how you're using your link cut trees, right? If you're using them in, say, blocking flow, then the very first step you're doing is you're doing n make trees anyway. So, you know, this is the dominant thing here, right? Because in blocking flow, m is the number of edges, so it's bigger than n. So m log squared is going to be bigger than n log n anyway. But yeah, it turns out, as you see on the p set, this log squared can get improved to log n. Same data structure, just better analysis of using splay trees. Any other questions? Okay, so that's all I wanted to say for for link cut trees. So if there are no more questions, then I'll switch to the second topic, which is min cost max flow. Yeah.
You ever mentioned to like add flow and subtract?
Yeah, so I didn't. Yeah. I mean, I'll just mention you can do those things using, basically by augmenting the binary search tree you're using inside of aux trees, right? So, right. So, how should I? Let me give you. So for example, you know, so your question is, how do you do things like add, subtract, flow? So maybe I'll say something about it, and I won't go into all the details. But the heart of it is basically augmented BSTs. which you'll use inside of your aux trees. Your aux trees will be augmented binary search trees. So suppose, for example, suppose I have n items which are, key value pairs, right? And I want to support operations like say sum of k returns sum of all values corresponding to keys that are all at most k. Right. And you want to support also insertion of key value pairs, deletion of them, and these sum operations, predecessor, et cetera. So you can do this kind of thing with BSTs by basically augmenting the nodes to contain subtree sums, right? And then as you're walking down the tree, you can use these subtree sums to get answers for this. So using this kind of idea, you can also implement those operations in the aux trees. So the basic idea is it's not going to be sum. Like the thing that you're applying, the operation you're applying is not sum. It's like a min operation, for example. So if you want to keep track of like min capacity. So kind of each node will contain the minimum capacity of all nodes in its subtree. And by manipulating these augmentations, you can handle all that. So yeah, you can think about it as an exercise, but I don't want to spend too much time on it. Any other questions? Yeah, good question, though, because I completely skipped it. Okay, so min cost max flow. So that's it for basic flow, max flow, right? So remember, we got into this whole link cut tree business because we were trying to speed up blocking flow. So how about another twist on max flow, which is min cost max flow. So min cost max flow. Each edge has not only a capacity, I'll call it U of E, but also a cost, C of E, which is possibly negative, possibly, or 0. So it's any real number, let's say. Actually, I'm going to, at some point, so let's just write capacities are in 1 up to U, capital U, and costs are in minus C up to C. So let's just say they're integers from minus capital C to capital C. And the goal is to find a max ST flow which minimizes the cost. And what's the cost? Let's call this flow F, which minimizes the cost of F, which is the sum over all edges of the flow on that edge times the cost of the edge. Okay, so just so we're clear, consider all flows F which are max flows. So we definitely want our flow to be a max flow. And amongst those, choose the one whose cost is minimal. And let me just write a little note here. In the residual graph, the reverse of edge E has costs. So remember what the residual, I'll fill this in right now, but remember what the residual graph is supposed to represent for us when we're doing flow computations. It's representing to us that we can push flow, we can augment flow along certain paths, right? So for example, if we had an edge with capacity 2, and so far in the flow we've built up, we're pushing one flow along that edge, then in the residual graph, it's still left with capacity 1, and the reverse edge is also now there with capacity 1, because we can send back that flow that's currently on it. So when you're dealing with costs, you have to be a little careful about costs in the residual graph. So what do you think the cost should be, right? So if you have an edge E that's appearing in the original graph, and there's still some residual capacity left on it, it'll still appear in the residual graph with the capacity that's left, as well as whatever the cost was. But the reverse edge will also appear, right? It'll appear with whatever amount of flow we're pushing on it, because we can send that flow back. But with what cost? Yeah, the negative, right? Because if you push that flow back, then you retrieve the cost that you paid. So just keep that in mind. It has cost minus C of E. Okay. So a related problem is a problem called min-cost circulation. What is a circulation? A circulation is a flow F such that flow in, so let's say inflow of V equals outflow of V for all V. So there's no source and sink, okay? You're just pushing flow around in cycles. That's a circulation. So what do I want to say about these two problems? Good. So okay. So claim min cost max flow and min cost circulation efficiently reduce to each other. So you only really need to focus on one. So proof. Suppose you can do min cost max flow. Why does that imply that you can do min cost circulation? So this is an easy one, maybe. Right? I give you a graph with capacities and costs. I tell you find me a minimum cost circulation. If you have an algorithm that already solves min cost max flow, why can you solve min cost circulation? What would you do? So someone gives you a graph G and says, find me the min cost circulation. What do you do?
I have a question.
Yeah.
For min cost circulation, are you saying I want that much flow? What's the minimum cost to achieve that much flow? Or is it just like the min cost for like any amount of flow?
So okay, so back to so let me make sure I'm using the right words for things. So a flow is just, or let's say, how do I want to say this?
Yeah, we just have zero flow and then we just have cost zero and we have a
Yeah, but cost can be negative,
Okay, so that's
right? So
but then if you have a cycle with negative cost, can you just have? Oh no, because then
there are capacities.
yeah, okay.
Yeah. So even if there are negative cost cycles, it doesn't mean that the problem's minus infinity or something. There are capacities involved,
Oh, okay. That's
right? So okay. So if you can solve MCC, how would you solve if you could solve min cost max flow, how would you solve min and cost circulation? Like how would you call this as a subroutine to solve this? First of all, this needs a source and a sink to call it, right? The definition of the problem involves a source and a sink, S and T. There's no source and sink here, right? So what do you do? You could, or you could just add a source and not connect it to anything. And you could also add a sink and not connect it to anything either. So the max flow in this graph is 0, right? Any ST flow in this graph is a circulation. And then you just find the min cost max flow in this graph, and it's a min cost circulation. Okay. How about this one? If I could solve min cost circulation, why does that mean I can solve min cost max flow?
Just add an edge from T to S, like increases capacity until you find the max flow capacity of the original graph.
Right. So okay, so yeah, you're saying add an edge from T to S, and try to find a min cost max flow. And then if you saturate that edge, it means you can achieve this flow. So I'll up the capacity by 1. And if I keep being able to saturate it, I can just keep increasing the capacity, right? So yeah, I think that's a good answer. So that says that if you can solve min cost circulation, you can solve this by calling this subroutine many times. The number of times we need to call it would be proportional to the actual max flow value. But I claim there's a way to do things where you only call it once. Yeah. Yeah, I think that actually. So yeah, maybe that's so. Add. Oh, is that actually what I want to do? So actually, no. So actually, I'm not. Now let me take back what I just said. So the problem is when you're calling the MCC algorithm, it doesn't really care about putting flow on that edge at all. It's just trying to find a circulation at minimum cost. So taking that circulation, which goes S to T and comes back, right? It might end up having some positive value. So it might not want to use it at all. It might instead want to use some other cycle in the graph somewhere else, right?
So it's not necessarily your max flow that you would get.
I'm sorry?
If you call MCC, you will not necessarily get the max flow.
Yeah, I mean, it might not want to use this edge back from T to S. So yeah, it has no incentive to create a max flow. Now that might be fixable by basically making the T to S edge have a very negative cost, so that it really likes to use it no matter what. I think that can work. So another thing that you can do is you can say, look, the very first thing I'll do. So maybe I should have written max flow plus MCC implies this. So the very first thing you do is just find any max flow. Don't care about costs at all. Just find a max flow. Okay. And now in your residual graph, find a min cost circulation. And when you do that, add that back to the original flow you found. So one thing you could do is, add T to S edge with very negative cost and infinite capacity. That's one thing you do. Or another thing you could do is find any max flow F in G, then find MCC F star. So notice that the difference of any two ST flows is a circulation. Okay?
As long as they have
The same S and T.
the same flow.
Oh, the same flow value. Yeah, sorry, that's right. Any two ST flows of the same flow value, their difference is a circulation. Okay. So that means if there's some other flow F star, which is the actual min cost max flow, then F star minus F will be a valid circulation in the residual graph. And then you can find it and then add it back to this back to the F. So find MCC in a residual graph. Then add it to F. Okay, good. So now let me look at MCC. So claim. So we want to be able to now find MCCs, min cost circulations, and one way to do it is, find. So let me propose an algorithm actually for MCC, and then we have to prove that it's correct. While there exists a negative cost cycle in the residual graph, augment along that cycle. That's the whole algorithm. How would you actually implement this algorithm? You need to figure out if there's a negative cost cycle and identify it. How would you do this? Do people remember some algorithm? Bellman-Ford. So you can implement negative cycle finding in time of Mn. This is Bellman-Ford. You can also do it even in O of time in O of m root n log c, essentially by some scaling algorithm. This is due to Goldberg in 95, I believe. So all the costs are between minus capital C and capital C. I believe it's in 95. Where did I write it? Yeah. This is also, with many hints, this is problem 2 on the current P set. Okay. Actually, I mean, this is shortest. This is single source shortest paths in graphs, in general graphs, where there might be negative edge weights. Okay, so Bellman-Ford gives you Mn, Goldberg gives you m root n log c. by a scaling algorithm. It's a little tricky, but I think I gave a lot of hints, so, and there are many parts. Okay, great. So the only question is, okay, so this is the algorithm. So there's a question of how fast or slow is it, and what's the runtime? That's the same thing. How fast or slow is it, and is it correct? Okay. Okay, so correctness. Okay. Say we have some circulation, some current circulation F, and optimal circulation in terms of cost is F star. Okay. So, and let's say that, suppose the cost of F star is strictly better than the cost of F. Okay. Then what can you tell me about F minus F star? F star minus F. What can you tell me about F star minus F? Or what are a couple things you can tell me about F star minus F? Yeah, it's negative cost. So if we augment by it, then we'll decrease our cost, right? And what else can you tell me about it? Well, I'll just tell you. It's a circulation. If you take two circulations and subtract them or add them, you get back a circulation, right? So is negative cost circulation, and it's feasible in our residual graph. Okay. Great. So if we're not at the optimal thing, it means our residual graph has a negative cost. It has a negative cost circulation. Well, we're not just looking for negative cost circulations. We're looking for negative cost cycles, right? But I claim that any circulation decomposes into kind of M cycles, basically. Basically, just like you can decompose flows into paths, right? You can decompose circulations into cycles. How? Start at any edge that has some positive flow on it, and then follow it around in a cycle. And then when you get back to the end of the cycle, record what the minimum capacity was on that cycle. And then extract that cycle out with that minimum capacity. Now what are you left with? You're left with, again, what you're left with is a circulation with one less edge. Because definitely at least one edge got saturated, right? So you can just keep doing this over and over again, pulling out cycles. You're decreasing the number of edges by one each time. So you can decompose any circulation into a collection of M cycles. And if the circulation in total is negative, it means one of those cycles is negative, right? So if you search for a negative cost cycle, so there will be a negative cost cycle, and you can augment by it. Okay. In fact, I mean, they had better all be negative, right? Otherwise, there's no point in including it in your circulation. Circulation decomposes into M cycles. So one of them is negative, we'll find it. Great. So what's our, actually let me just write it right here. What's our runtime? So we need, in each iteration, we need to run, say, Bellman-Ford. Or we could run the other one. How many iterations can there be? I mean, give me any valid bound.
MC.
MC. Let me think. Is that right? So yeah, because you're saying we decrease the cost by at least 1. So I think you need to add something else there, not just MC, but MUC maybe. Right? So every time we do this augmentation, we decrease the cost by at least 1. You know, how low could the cost possibly be? Well, there are M edges. They each have capacity at most U, and the cost is at least negative C. So the number of times we can decrease the cost is at most MUC. So I think O of Mn times MUC. So this is a pseudo-polynomial time algorithm. Kind of like the Ford-Fulkerson of min-cost circulation. Okay. So let's try to do better. Before I do better, I want to define something. So definition. A price function, or P, which maps the vertices into the real numbers, induces a reduced cost function. So let's say we have an edge UV. Okay. Its reduced cost is the old cost, the original cost of the edge, plus the price of V minus the price of U. Okay. What did I want to tell you? Oh, actually, plus PU minus PV. So the way to think about this is, let's say that we are buying gold at vertex U. Okay, so we have to pay to buy it. That costs whatever the price of gold is at vertex U. We have to pay to ship it to V. And then when we sell it at V, we make money, which means negative cost. So that's how you should think of this. And claim F is an optimal min-cost circulation if and only if there exists a price function P in the residual graph. Let's call it the residual graph is G sub F, such that all reduced costs are non-negative. So proof. So let's do one direction. Suppose there exists such a price function, such that all the reduced costs are non-negative. I have a question for you. What's the cost of a cycle using the original cost function versus using the reduced cost function? It's the same, because these PUs and PVs cancel along the cycle. So costs of cycles don't change when you use reduced costs. And we know from before that we're optimal when there are no more negative cycles, right, in the residual graph. So if there is such a P, well, every reduced cost is non-negative, which means that the reduced cost of every cycle is non-negative, which means that the cost of every cycle is non-negative. How about the other direction? Suppose GF has no negative cycles. So I'll just tell you what you would do here. Introduce a new vertex S with zero cost edges to everyone. Now define the price of U as just being the shortest path distance under the costs from S to U. This is the shortest path length from S to U. That's well defined because there are no negative cycles. You can show just by basically triangle inequality that this thing is a valid price function. I mean, not valid, but this thing as a price function will satisfy that all of these things are non-negative. That's the triangle inequality. Okay, so I'll let you think about that offline. Triangle inequality implies CP is at least 0 everywhere. So you can work that out. Okay, so now, good. So now let's look at faster min cost max flow. So a simple case. Let's say there are no negative cycles, negative cost cycles, and all capacities, all edge capacities are 1. So this U is 1. Actually, let me make it even simpler. And let me just say there are no negative edges at all. Okay. Here's going to be an algorithm. Find the shortest ST path according to costs, using costs as your edge lengths in the residual graph, and augment along that path. Okay. So the claim is that this thing is correct. So first of all, the runtime at most n iterations. And you can use Dijkstra in each iteration because edges are going to be non-negative. Well, they're definitely non-negative in the beginning, and we're going to see that even in future iterations, they're going to remain non-negative, even in the residual graph. Remember that we negate costs in the residual graph, right? So it's not clear a priori that they remain non-negative in the residual graph. But we're going to see that that is true. O of m log n per iteration. This is Dijkstra. So that implies that the total time is O of mn plus n squared log n. Dijkstra with Fibonacci heaps. So the claim is that there would never be negative cost edges in the residual graph. What's the proof? Right. So remember, this is a unit capacity graph. Right. So what set prices as PV is the shortest path distance from S to V in the residual graph. I should say negative cycles. Okay. Okay, good. So any edge we augment along is in a shortest path. Right? We only augment along shortest paths. And if an edge is part of a shortest path, if the edge UV is part of a shortest path, right, that means that the weight of the edge UV plus the distance to U is equal to the distance to V. Right? That's the property of shortest paths. Right? Let me basically move this over here. The distance to V, if UV is part of the shortest path to V, then the distance to V is equal to the distance to U plus the cost of the edge UV, which means that the reduced cost is 0. Right? So any edge we augment along is in the shortest path, which implies that its reduced cost is 0. And when we augment along it, that means that it's saturated, because it's a unit capacity graph, and the reverse edge will be put in the residual graph with negative cost. But negative of 0 is 0. Okay. So the edges that we introduce, the new edges that we introduce into the residual graph will never be negative, right? So in fact, we'll never even have negative reduced cost. Negative reduced costs. That's what I really should say. We'll never have negative reduced costs in the residual graph. Implies that when we add any new edge to the residual graph, it's the reverse of a saturated edge, which implies that its reduced cost was 0. So any edges we add in the residual graph will never be negative. And I think I'm out of time, so there's not much more to say. But I think I'll just augment a couple of paragraphs at the end of this in the notes. Okay, and you can look at the notes for the remaining part of the argument. But questions about anything I said up to this point? And then one of the p-set problems is going to be using scaling to basically let you use not just unit capacities, but arbitrary capacities.
What about negative cycles?
I'm sorry?
Well, this is
Oh, you're saying what if the graph originally does have negative cycles? So if the graph originally does have negative cycles, basically what you do is first you find any max flow, okay? And then now you just need to find a min-cost circulation, right? So that graph, now you need to find a min-cost circulation. It might have some negative cycles in it. In fact, it better have negative cycles, otherwise there's no point in finding a min-cost circulation. So what you're going to do is just look at any negative edge. Forget about cycles. Just look at any negative edge and just fully saturate that edge with flow. That's not going to be a valid circulation, So now you need to turn this into a valid circulation. But by fully saturating certain edges, what you've done is some flows have extra flow coming in and some flows have extra flow coming out. And you need to fix that. You need to basically send the flow back to where it came from. So what you'll do is you'll create a new source in sync, connect the source to everyone who needs to push flow out of them, and then everyone who needs to push, everyone else you connect them to T, and you set up the capacities in such a way that the capacity is equal to exactly how much flow I need to push out of me. And now you try to find a min cost max flow in that graph. But that graph has all positive costs or non-negative costs. And then you can use basically this. So I know that went kind of fast, but
So you end up with the same runtime?
no, you'll end up with, in unit capacity graphs, you won't have this terrible MUC kind of runtime. You'll have something that's actually strongly polynomial. But you can speed it up using scaling, but then you have like a log U dependence. So the scaling by U you'll see in the note, you'll see on the P set, and I'll complete this in the notes. I think we're very out of time. So.